going to be introducing my project. These are all my group members. We have Paris Williams, Tony Wright, me, and then Reagan Howe. So our group project was over Avogadro's number. So Avogadro's number is a fundamental constant that tells us how many particles, atoms, molecules, or ions exist in 1 mole of a substance. The Avogadro number is 6.022 times 10 to the 23rd power. Some relevant fields would be atomic theory, mole concept, and molecular chemistry, um, molar relationships, and then stoichiometry. And then a relevant scientist was, of course, Avogadro himself. His full name is very long. I would pronounce it, but I don't know if I can. And then his nationality was Italian. His professions were a physicist and a mathematician. Some contributions that he did include differentiating atoms and molecules, molecular formulas, and etc. A major contribution that he did was in 1811. He proposed what became known as his hypothesis, which was equal volume of gases at the same temperature and pressure contain an equal number of molecules. Some fun facts about Avogadro was that he held a professorship as a teacher at the University of Turin, and he was also a nobleman, and he held the title count, but he was reportedly a modest man. And another fun fact is that only one known portrait of Avogadro exists. We're not sure if there's any more, but that portrait right there that you see on the slide is the only one that I could find. And then, yeah. For the original experimental process, he did not directly create the number that he's known for. Instead, he proposed an idea in 1811, and his idea was equal volumes of gases at the same temperature and pressure contain the same number of particles. He used this to help formulate and explain results from chemical reactions and gas experiments. His process was theoretical based on comparative gas volumes and how they reacted, especially combining hydrogen and oxygen to form water. So here is an example of his work. So it was 2 liters of hydrogen plus 1 liter of oxygen equals 2 liters of water vapor. This didn't make sense unless gases were made of molecules, not just atoms. He proposed that gases like hydrogen and oxygen existed as diatomic molecules, which helped explain the reaction ratios. So some difficulties and complications about Avogadro's experiment was that it was difficult for him because at the time period, the idea of molecules was not widely accepted. A lot of the scientific community struggled to grasp the concept of atoms. Avogadro's work was ignored for decades because he didn't have strong experimental proof and was not actively promoted to other scientists. Also, because since he was from Italy, which wasn't known for science at the time, his work was published in French, making it difficult for other scientists to decipher it. So they tried, but ultimately they couldn't because they didn't understand, and it wasn't until years later when people actually understood his work and Avogadro's number came out of it. So the motivation for his experiment, he wanted to clarify the process of how gases combine in simple volume ratios. He was inspired by other chemists such as John Dalton and Joseph Gay-Lussac. He used their theories to help him explain gas behavior more clearly. During this time period, the terms atoms and molecules were used to describe the same thing. However, with the help of his research, the two terms became defined separately. And then the original benefits of the discovery was during this time period, the terms atoms and molecules were used to describe the same thing. However, with the help of his research, the two terms became defined separately, as I said before. Not only that, but he also helped in the development of the atomic mass scale. So chemists could now correctly calculate the atomic masses of elements. With the help of his work, actually, Dmitri Mendeleev created the periodic table, which is widely used in the present. So, thank you so much.
3.1 The modern experimental process described. Scientists today find Avogadro's number by counting the atoms in a pure ball of silicon. It is known as silicon 28. They use X-ray machines and laser tools to see how far apart the atoms are and how big the ball is. By being able to see this, they're able to know how many atoms are inside, and essentially gives the number of atoms in 1 mole, which is 6.022 times 10 to the 23rd power. 3.2, the differences in modern approach outline. The scientists use chemical reactions or gases to estimate his number. Although now, due to the advancement in technology, they are able to measure everything directly by using physics and the correct tools. They are able to measure real atoms in crystals. 3.3, the modern benefits discovery. In order to help everything go really smoothly, having the exact number helps everyone out a lot. The chemists know how many atoms or molecules are in a substance. This is extremely helpful when it comes to medicine and materials as well as engineering. They're even able to understand everything clear as possible to where they speak the same language, which you can call science language. And lastly, 3.4, the future expectations of research. They want to be able to get things more accurate than what they already have, as well as faster. They will have better quantum tools and better lasers. This will be able to help with research as well as new medical opportunities that may surface in the near future as things continue to evolve.
Hi, my name is Paris, and me and my group members are doing a project on Avogadro's number. 4.1. How does Avogadro's number bridge seemingly disparate worlds of the macroscopic quantities we measure in the lab and the microscopic realm of individual atoms and molecules, and why is this connection fundamental to the field in chemistry? Avogadro's number is a cornerstone concept in chemistry, meaning it directly links the mole, standard unit for the amount of substance, to the actual number of constituent particles, atoms, molecules, ions, etc. Understanding the connection is crucial for performing stoichiometric calculations. Without Avogadro's number, we wouldn't be able to relate the weights of substances we work with in the lab to the number of atoms or molecules involved. 4.2. Understanding the answer to this question provides several key benefits. It moves beyond simply memorizing the value of Avogadro's number. A solid grasp of connection makes stoichiometric calculations and understanding concentration units more intuitive. It also highlights how chemistry is not just about qualitative observations, but also about precise measurements. This understanding is essential for grasping more advanced concepts in physical chemistry, such as kinesthetics. 4.3. The process of writing this question involved identifying core concepts, focusing on the why, and highlighting connections while emphasizing the importance of the all. Avogadro's number was the given topic. Instead of asking what is Avogadro's number, the goal was to explore its significance. The question specifically aims to connect the macroscopic and microscopic worlds. 4.4. The question encourages a discussion of the conceptual link it provides rather than just a factual recall. It prompts the learner to think about the implications of this number for the practice of chemistry and its theoretical underpinnings. It moves beyond the what to the how and why of Avogadro's number. Thank you.
Hi, I'm Reagan, and this this is for the physics project Avogadro's number. I did section 5, and I'm going to be presenting on section 6 as well. So section 5 is a question and solution. My question is, how many atoms would you have in total if you had 1 mole of every element on the periodic table? Now, considering Avogadro's number, its symbol is Na, and this arrow here, if it'll show up, doesn't really want to. Or maybe going at another angle. Na, the arrow between them is a subscript, but Avogadro's number is 6.022 times 10 to the 23. And there are 118 elements on the periodic table. So if we multiply Avogadro's number by 118 to get 7.12 times 10 to the 25, that's how many atoms we will have. Now, it may seem simple, and that is because it is. Avogadro's number is just the number of atoms in 1 mole. So to find the number of atoms, instead of dividing, you multiply. Now, things that other people might find interesting about Avogadro's number is that it wasn't really discovered by Avogadro. The constant was named long after his death. And fun fact, he used to be a lawyer before he became a physicist. He'd earned a law degree before his switch to science. Now, he didn't necessarily collaborate with any other scientist. However, his ideas did branch off of Dalton and Gay-Lussac's theories, and his work was a response to their ideas. It took almost 50 years for Avogadro's work to be fully experimented and accepted by the community, and his hypothesis started in 1811, and it wasn't until 1860 when Stanislao Cannizzaro presented his work that his ideas started to gain traction. What surprised our group is that originally we'd expected Avogadro to have been widely known. However, it was the opposite. For decades, his theorems were ignored, and we were also surprised that the actual Avogadro number wasn't calculated by him, but rather from the result of other scientists' work. What we did not find, but wanted to, is that we would have liked to see more portraits of him. We didn't find many pictures or paintings about him. We've simply found one, and there's very little information on his life, and we were missing letters, opinions, papers that he's written. We didn't have any of that. However, if we'd had more time, we'd look into the history of how exactly scientists came up with Avogadro's number, or whether or not his work or reading was easy or difficult. Computer. Another topic we recommend exploring is the standard model of particle physics. And the reason why is that Avogadro's number is quite important in relation to particles like protons, neutrons, and electrons. And our overall summary of our topic is that Avogadro's number turned out to be more than just a number. It provided so much knowledge to modern-day chemistry, and that was the reason why we can tell the difference between molecules and atoms. The project development was very well done overall, and the group divided their roles perfectly. I think everyone did a wonderful job keeping up with their tasks. It was all brought in on time, and was all consistent and flowing, and if I had to work with another team again, I would choose this one. Everyone was crucial. Everyone was important. And nobody felt left out or like they weren't doing enough. Now I'd say The most important part of this number is understanding that it was created as a bridge between the macroscopic and the microscopic world. Thank you.